Okay, so the next question that we will solve is 2b. So question 2b, this says table QB or Q2, this is table Q2, is a state transition table for a finite state machine whose input is denoted by X. So these are the inputs. Reduce the number of states in the state transition table from 6 states to 2 states using row matching technique. Okay, so let's start. 2b1. So we are going to make use of row matching. According to row matching, 2 states are equivalent if they have the same outputs and they so have the same next states. If you look at all these ones now, these are the next states here. These are the next states, next state, next state, next state, and these are the outputs. If you look at A, for instance, this is ED as its next state and output of 0. Is there any other row that has ED0? You notice C also has ED0. So we can replace C with A. So we can actually remove this line, and anywhere we see C, replace it with A. So we're going to have something like this. And do we have any other ED? We don't really have any other ED, that's all. So anywhere we see C, we have A in place. Anywhere we see C, we have A in place. Now after making this these adjustments, so we have A here now, we have A here, we have A here now. So since the three of them have A and they all have output of 1, so we can replace all of them with just B. So F, we are going to replace this with B. Since it has this one also has A1, we replace it with B. So anywhere we see D and F, we replace it with B. So this is D, we replace it with B. What else? F, we replace it with B. And yeah, so let me draw what we are going to have after this. We are going to have PS NS X equals to 0, or even before, we can actually do all rough workings on this one here. So now here now we have EB, so that is E. Now we can actually replace E also, since we have EB0, we can replace E with A. So anywhere we see E, we replace it with A. So we've cancelled all these ones. C, we replace it with A. So the only thing we have left is just AB, AA, BA01. So that's the reduced states. So since they said we should reduce it to just 2 states, so that's the 2 states now. So X equals to 0, X equals to 1, and the outputs. So we have AB, we have A, B, A, 0, 1. So one way to confirm your answer is if all the next states that you have here is the same thing as what you have here. So that means it's correct. Now that's the first part of the question. The second part of the question says encode the reduced states using one hot encoding. So according to one hot encoding, only one of those bits is going to be 1. So possible value is 1 0. So one of those states is going to take 1 0, the other one is going to take 0 1. In as much as in this bits only one is 1, only one is 1 here. So that's one hot encoding. So we can basically just say 2b A is equals to 0 1 and B is equals to 1 0. So we can replace A with this one inside this table, so that we have PS X equals to 0, X equals to 1. We have outputs. We've replaced A with 0 1 now and B with 1 0. X is A is 1 0 1, B is 1 0 0 1 0 1, and so this is what we have as our table. So we can expand this table from here. So if we are expanding the table, we are going to have let's say capital letter A, B, and X. And for this one, we are going to have 0 1 0 1 when x equals to 0, 0 1 when x equals to 1. Then we're also going to have 1 0 when x equals to 0, 1 0 when x equals to 1. So the next thing we should need is our next states, which is A and B. So that will be the next state. So when you have 0 1 and x is 0, 0 1 x is 0, so the next state is 0 1, 0 1 x is 1, 0 1 x is 1, the next state is 1 0. Then when you have 1 0 x is 0, the next state is 0 1, then 0 1 also here. So are we asked to make use of any flip-flop? So this question solves the part where we're asked to encode. This is the encoding part. Now this part I've already started solving the last part already, where it says based on the encoding done in this, develop a D flip-flop based circuit excitation table for the machine. So this is what we are doing now, the excitation table. So this is 2B4. So the encoding just stops here. So now we have DA, DB. Now what we need now is to reduce to, so what we need now is to get the value of this DA and DB. So we know DA is always going to be equals to the next state of A, so that's going to be 0 1 0 0, and DB is also going to be 1 0 1 1, and the output is going to be 0 0. So now if you notice here, we only have one output for when s equals to 0 and s equals to 1. So when s equals to 0, the output is 0. When x equals to 1, the output is also 0 for 0 1. So for 1 0 also, we have only single output for when s equals to 0, x equals to 1. So in that case, we are going to have 1 1. So based on this table now, we need to get our expression. So it's not easy for us to make use of K-map in this case because we don't really have a complete table, but we can still generate the expression from here. Okay, so to develop the expression of this one, we'll take a look at DA. If you notice in DA, only one of them is 1. So one of them is 1, and the corresponding value that is also 1 in the present state, so this is the present state here, is B and X. So DA is going to be the combination of B and X, since they are the one that are 1. So that's just it. So for DB, we know we have a 1 here, and where we have a 1 here is B. So we always pick X alongside, like anytime you are picking the one that is 1, you pick X alongside it. So now we have for DB, we have B to be 1, so put B down, and X bar here, so X bar, so just 1 0. So you always pick, so you know this is one hot encoding, you always pick the 1 and the X in your expression. So but we also have another one here, we have DB here, where A is 1, so that will be plus A, X is 0, X bar, the last one is plus A is 1 and X, right? So we can actually simplify this further by saying DB is equal to BX bar plus A open bracket X plus X bar. So X plus X bar is going to 1. So DB is equals to bx bar plus a. And so that's going to be that 1 2. So the last one is our output y. So if we look at output y, we have 1 here. So where we have 1, we have a is also 1 here, and x is 0, x bar. We have a to be 1 and x to be 1 also, plus a x. So we can factorize this further and say this is a x bar plus x, which is equals to a. So that's dA is equals to bx, dB is equals to bx bar plus a, and y is equals to a. So I'm not going to be drawing the logic circuit of this one. You can basically just draw that yourself. So that's I think that should be the end of this question. Yeah, so the next thing we just need to do is to sketch the logic circuits, and I'm not going to be sketching that. Or should we? Okay, let's do it. So we have two flip-flops. The dB, so we have dB. So dB, we are going to need a clock. We are going to need a clock. We are going to need QA bar, QB bar. And so we are going to have a line for clock, a line for the input x. So for the clock now, we are going to share this for them. The clock, we'll share this. Okay, now, so for dA, we know d is equals to bx. So we have an AND gate there. So we have a line for bx, which is going to go like this. And that's for x. So we need a b. We can bring b all the way up like this. So that's going to give us dA, which is bx. So for dB is an OR gate. So dB is bx bar plus a. dB dx bar, bx bar, and that's going to be b. Oh, sorry, we are going to have an AND gate. We are going to have an AND gate there. So the AND gate we are going to have is bx bar, yes. So that's going to be, this is line B, and we can have a bar here. That's bx bar, and the other one is a. So our output is also equals to a. So we can have, this is our output y. So that's the circuit. Thank you. So that's the end of this question.